Hi everyone, my name is Mohammed Iqbaria from the Technion, and I will present my paper, Predicting Execution Times with Partial Simulations in Virtual Memory Research, Why and How. This is a joint work with Idan Yaniv, Jainil Gandhi, and Dan Safrir, my advisor. Before we start, I would like to note that while architecture papers typically propose some new architecture improvement, our work is a bit different. We propose to improve upon the methodology that is used to evaluate such newly proposed architecture improvements. More specifically, we propose to improve the methodology used when conducting virtual memory research. As we all know, for every memory access, 64-bit x86 processors must translate a virtual address to the corresponding physical address. The CPU first searches the TLB, which caches recent translations. If the TLB misses, then the CPU must walk the page table hierarchy, which incurs several additional memory accesses. This address translation overhead might account for up to 83% of the execution time for memory-intensive workloads. Many studies try to mitigate the address translation overhead. As an example, let's consider an ISCA study from 2013, which proposed direct segments, which were able to eliminate most of the TLB misses for big memory workloads. The question that the authors of the paper should answer is, what are the performance benefits of direct segments? This question, how to evaluate the performance of newly proposed architecture improvement, applies to any virtual memory study that proposes such an improvement. It goes without saying that building a prototype of the new hardware in order to answer the question is usually not feasible. So researchers typically employ one of two simulation methodologies. The first is full or cycle accurate simulation, using something like Gem5. Full simulators reproduce the entire CPU cycle by cycle, so they are relatively slow. For example, simulating 1 minute of execution of real CPU might take an entire year. The other alternative is partial simulation, namely simulating only part of the system. For example, the direct segment study from ISCA 2013 simulated only the modified TLB and calculated the resulting TLB misses reduction. Partial simulators are much faster, but they have an inherent drawback as compared to the full simulators. They don't report the bottom line runtime. To overcome this limitation, the ISCA 2013 researchers defined a model that predicts the runtime from TLB misses. The model assumes that runtime is a linear function of the TLB misses. That is, runtime equals some alpha times the TLB misses plus some beta. In this case, alpha is the latency observing a single TLB miss, and beta is the ideal runtime when the TLB miss rate is 0. Quite a few virtual memory studies use this methodology over the last few years. Their exact specification of the model slightly varies across studies. For example, some models take the number of cycles spent on page walks as their input instead of the number of TLB misses. However, all models have one thing in common. They assume a linear relationship between the input TLB metric and the runtime. This scheme helps visualizing how architects define and use their models. The x-axis is the model's input, which can be the number of page walk cycles or TLB misses, for example. The y-axis is the model's output, which is the runtime, namely the total execution cycles. To define the model, we need to find the two parameters, alpha and beta. Doing this is relatively straightforward if we have 2 points on the linear curve. And the previous studies obtained these points by simply measuring them on a real processor with either regular 4K pages or 2 mega huge pages. The model is defined as the linear curve that passes through the two experimental measurements. To get the predicted runtime of the newly proposed hardware, all one has to do is plug in the simulated number of TLB misses into the model. The problem with these models is that they were never validated, and we ask, should we trust the models? Do processors really behave this way? Can the runtime really be expressed as a linear function of some TLB metric? How can we tell? How can we answer these questions? Our first insight is that previous studies could not answer these questions because they had only 2 points measured with either 4K or 2 mega pages. Because these 2 points are used for fitting, no data remains for validation. Our second insight is that we can obtain many more data samples if we mix regular pages and huge pages in the same address space. To this end, we developed Mosalloc, the mosaic memory allocator, which combines multiple page sizes in the same address space in a carefully controlled manner. Mosalloc intercepts all memory allocation requests and serves them with a user-defined mixture of page sizes. Mosalloc can link against any Linux application running on 64-bit x86 processors without modifying or rebuilding the application. We will not describe how Mosalloc is implemented in the interest of time, but you can find the details in the paper. Graphically, Mosalloc allows us to test the pre-existing runtime models, which are defined by only 2 points, against dozens of new experimental points. As noted, Mosalloc allows us to back the address space with arbitrary combinations of regular pages and huge pages. But it only does as it is told. It does not find quote-unquote interesting memory layouts that produce data points that are scattered throughout the x-axis. Our system therefore has a second component, whose job is to generate page mixtures that are diverse enough. We first try to use random Mosalloc layouts that entirely consist of 4K pages, along with a single huge page window that has some random size and is positioned in some random location. We learned, however, that random sampling is not effective for generating diversity. The reason is that for most workloads, TLB misses tend to be concentrated in a relatively small hot region. For example, 50% of the TLB misses of the MCF benchmark originate from contiguous 12 megabyte region. Consequently, as illustrated in this figure, most randomly generated layouts miss the hot region and therefore roughly perform similarly to using only 4K pages. To overcome this problem, our layout generator algorithm diversifies the points as follows. First, we identify the hot region location and size by running the benchmark and using Intel's precise event-based sampling. Then, we create a huge page window of the same size, and we systematically slide it over the hot region, gradually covering a larger fraction of it. We found that this method yields the most diverse memory layouts in terms of where they are positioned in runtime TLB metric plane. And now, let's see some results from using Mosalloc and our layout generator. So as noted, with the help of Mosalloc, we collect many more experimental points than the 2 used in previous studies. The new points are the blue circles in this figure. The x-axis shows cycles spent on page table walks in each run, as measured by the CPU performance counters. The y-axis is the runtime, or the total execution cycles, which is also measured with the CPU performance counters. We see that the new data indicates that for some workloads, a linear runtime model is suitable. However, for other workloads, our new data reveals an nonlinear pattern. A question that follows is then, why do the samples exhibit this nonlinear pattern? Which seems to suggest that a higher order polynomial function is probably needed in order to make the model more accurate. The reason is that when TLB miss rate is high, the CPU must work harder, so to speak, speculate more, etc., in order to hide the latency of the page table walks. As the TLB miss rate drops, the CPU becomes more effective in hiding the table walk penalty. In this example, when TLB miss rates are higher, the slope of the curve is 1.4, which means that every cycle spent on walking the page table adds 1.4 cycles to the overall runtime on average. When the misses become less frequent gradually, the out-of-order execution becomes more efficient, and the slope of the curve decreases to 0.4, namely a penalty of less than half cycle per miss on average. Another interesting observation is that the slope can be greater than 1 when using the table walk cycles as the TLB metric. For instance, this example shows that the Zalan benchmark has a slope of roughly 2. This result is surprising, because it means that every cycle spent on walking the page table adds 2 cycles to the overall runtime. How can this be? Previous models understandably did not consider such scenarios, because they intuitively assumed that the worst case scenario is when TLB misses stall the CPU completely, and then the slope is 1. It indeed seems strange that a page walk stalls the CPU by more cycles than the page walk takes. This reason this happens is because page table entries are cached by the CPU data caches, so they contend with the application data. This table highlights that cache contention is in fact caused by the competition between the page walker and the application. Here we see that the number of cache references made by the page walker when 4K and 2 mega pages are used. As expected, the 4K configuration suffers from more page walker accesses because it experiences a higher TLB miss rate and so must walk more page table entries. Now we additionally see the number of cache references made by the program itself, excluding any page walker accesses. Seemingly, a running program should generate exactly the same memory references sequence, regardless of whether it's backed by 4K or 2 mega pages. But we can clearly see that the 4K configuration experiences more LF references than the 2 mega configuration. This happens exactly because the data caches house more page table data in the 4K run. And now, let's see how we tested the accuracy of previously suggested models. We tested 19 benchmarks from several suites. From each suite, we used only TLB-sensitive benchmarks, whose runtime changes by at least 5% when backed with 1 giga huge pages. We ran each benchmark on 3 Intel platforms to examine the effect of using different virtual memory microarchitectural designs. The TLB of Sandy Bridge contained 512 entries, a number that was doubled in Haswell and tripled in Broadwell. Also, starting at Broadwell, Intel processors are equipped with 2 page table walkers to handle TLB misses concurrently. We used Mosalloc to run each benchmark backed by dozens of different memory layouts that mix page sizes. In each run, we measure the runtime, the TLB hits and misses, and the page table walk cycles. Together, these measurements provide us with the data needed for putting the previous model to the test. We compare the experimental samples against the model predictions to calculate the absolute percentage error of each sample. Then, for each model, we show the maximal error across all the benchmark executions across all machines. More detailed results can be found in the paper. Here are the results. The x-axis lists the linear models named by their developers, Pham, Basu, Gandhi, Alam, and Yaniv. And the y-axis shows the maximal per model error across all benchmarks and machines. We see that the errors can be quite high, ranging from more than 20 to nearly 200%. So now that we know that the previous models are not as accurate as we hoped, the question is, can we do better? Thanks to Mosalloc, the answer is yes. The first step is to fit the new model against all the data points we have, in contrast to the previous models, which used only 2 points and were therefore linear by design. As we saw previously, the runtime pattern of some workloads behaves like a nonlinear polynomial function of the TLB metric. Our experiments taught us that a polynomial degree of 3 is flexible enough to accurately capture the behavior of all the benchmarks. The second step towards more accurate models is choosing the right input. We found that some workloads are best predicted by C, the page walk cycles, while other workloads are best predicted by M, the TLB misses, or H, the TLB hits. Mathematically, it sounds reasonable to take all 3 inputs, H, M, and C, and let the model to use all of them using a polynomial of 3 variables. However, if we do that, the resulting model will be too flexible and therefore might suffer from overfitting. We therefore employed the lasso regularization method, which chooses the optimal input and zeros the other variables. We call this model Mosmodel. To summarize, Mosmodel is a new polynomial runtime model of degree 3, which takes 3 variables, H, M, and C. This model has 20 coefficients, which makes it prone to overfitting. So we use the lasso regularization method to choose only the most useful coefficients and zero the rest. We additionally generate enough samples with Mosalloc to ensure no overfitting occurs. We validated Mosmodel in the same way as the previous models and found that Mosmodel succeeds to bound the maximal relative error below 3%. Note that Mosmodel also performs better than the second and third degree polynomial models. To conclude, in this work, we developed an improved methodology for evaluating newly suggested virtual memory designs. To use this methodology, you should first collect experimental samples with Mosalloc and use them to build Mosmodel. Then you should use Mosmodel to predict the runtime, given the output of the partial simulation that implements your new idea. This would allow you quickly and accurately assess the benefit of your idea. Mosalloc and Mosmodel are open source and available through this URL. We welcome your comments and contributions. Thanks for listening.